Okay. Hello, everyone. I'm Nirmaldo, and today I have joining me physicist Stephen Shu and Jonathan Oppenheim. So, welcome, guys. Steve has recently published a theoretical physics paper whose idea came not from his mind or from the mind of any human, but from the mind of AI, which makes it the first such theoretical physics paper. Jonathan, on the other hand, has critiqued this paper and he has said that AI's first big physics outing could be, in fact, wrong. And he has also warned us about the possible proliferation of AI slop in physics. So we will discuss all of that today. But let me make the introductions properly first. So Steve is a professor of physics at Michigan State University. He is also a tech entrepreneur, and he is a co-founder of AI-linked startups such as Superfocus AI and Genomic Prediction. And he has interested in a lot of areas of physics, starting from quantum gravity to QCD, cosmology, foundations of quantum mechanics. Jonathan is a professor of physics at University College London. He works in quantum information theory and quantum gravity. So today we will discuss the broader topic of AI in physics, and also about take as a case study Steve's paper, which is on nonlinear quantum mechanics. So we'll discuss that. All the links to Steve's paper, Jonathan's preprint, his blog post will be in the description below. My first question is for both of you, and I will start with you, Jonathan. How much are you using AI in your day-to-day work?
I mean, mostly, I feel like I mostly use it to test it out. So I have a few questions that every time a new model comes out, I give it a try, and see if it's improved and whether it can solve these, a few problems that I know the answer to because my students have solved them, and but they're not published anywhere. So I know that they're, unlikely to be in its training data. And so I mostly just want to familiarize myself with the models and how they work and see if I can get them to do what I want. But I also do use it for, like, I find it useful for getting feedback on a paper, especially if it's normative feedback. Like, would a expert in quantum information theory understand this paper? Would an expert in quantum gravity understand this paper? Or I've especially just actually, the last paper I put on the archive, in response to Steve's paper, I asked it to do a round of refereeing, and actually that was incredibly useful. So I asked it to pretend to be the editor. I asked it to choose three referees, and even name them. And then I asked it to give me three referee reports, and it was like a reasonable refereeing, actually, and useful. And I did edit the paper as a result. So I also use it for literature searching sometimes, but with care, and for, like, tutoring. If I want to learn something that is outside my wheelhouse, I find it very useful. If it's something that I'm already familiar with, I find it less useful. But for things that I'm not expert in, I find it great.
So you said you give AI some problems that you have beforehand. And how do you see it faring? Like, is it progressing? Is it getting better at solving those problems, or is it failing still?
I mean, the progress is astounding, but it's also terrible. So I find, like, it used to not know how many R's were in strawberry, and now it can pretend to do a calculation. And I guess what interests me is, how, like, what I guess I find difficult is that it's very confident and often wrong. So it's very difficult for you to verify it. So I guess what I'm interested in exploring is how can we verify these models? But the improvement is astounding. And I think if you're not, maybe that's something that is very apparent to people that are in physics in particular, or coding, and, things where you see the improvement. I haven't necessarily noticed a huge improvement in editing, but the improvement in mathematics is pretty astounding. I don't know how long it will last, but it does seem to be doing something which is not in its training data. I I do think, like, so we're working on something which is where it's particularly bad at. So we work on a theory which is neither quantum field theory nor classical field theory. It's just one of these hybrid things, and that means it's adjacent to a lot of stuff that's in its training data. And I think that's where it's particularly bad, because it's drawn to what it's been trained on and not this new thing. And so it's really terrible on the sorts of problems we're most interested in, which, so it's interesting to try and figure out how you can correct it or if you can correct it or anything like that. So that's, I guess, my interest. But the improvement is incredible.
Steve, your take on this?
I agree with everything Jonathan said. I would add a little bit, I guess, maybe that about things that I've done that maybe he hasn't spent so much time on. So I spent a lot of time on something I call the generate verify kind of
Mhm,
pipeline.
mhm,
And in doing that, typically, I've both done this just by hand, like sort of cutting and pasting the output of one model and feeding it to another model with a prompt to be critical and analyze it and find all the logical gaps and things like that. So I've done that manually, and I've also built a uh, kind of demo. I was sort of forced to do this because I was working with one of the big labs, and the person sort of in charge wanted to actually see it in action, not just my description of my own, like doing it by hand. So I actually even built like a kind of demo which automates this process to some extent. And the origin of this is that number one, like the way a particular model prompted in a particular way makes mistakes could be different from the way perhaps a totally different model, which was trained differently, or maybe the same model, which has been prompted differently, will react to the same information. And I find there is some, okay, I guess the weakest way to put it is the mistakes that are made in this context are not 100% correlated. So by chaining things together, you can sort of cancel out errors to some extent. That's the sort of weakest way to put it. Um, a stronger way of putting it maybe is to say something, just to point to an actual empirical example, which is that in a lot of the efforts to write proofs, which is quite a difficult thing for IMO problems, International Math Olympiad problems, the researchers who did that, one team that I actually interviewed, one guy that I actually interviewed on my podcast, who has a physics background actually, although he's a CS professor, they use this generate verify chain, and they were able to get all of the leading frontier models, not even the best ones today, but the ones circa last summer ish. They were able to get all of them to perform at the gold medal level on the latest set of 6 problems, which presumably are not in the training data. Um, by chaining the process the way I described, however, if they just one shot, so if they just went to a particular model and said, hey, even in deep think, deep research mode, write a proof for this problem, the success rate was probably 20 1/5 as high as, instead of 5 out of 6, it might have been 1 out of 6. So I think the stronger case to be made is that you can qualitatively increase the quality of the final output. Like you don't look inside while it's doing, the models are talking to each other doing this thing, but you just look at the final output and you compare that to just a one shot result, which is probably what most people in our community have seen. Like everybody's kind of fooled around with the models to some extent and has seen one shot outputs, which could be really hilariously bad, as Jonathan said, or sometimes spot on. But when you chain things together, the claim is that you can often get kind of not, maybe almost order of magnitude, in some sense, order of magnitude improvement. So I've been quite interested in that. There's a team at DeepMind that actually wrote a whole paper called the model that they built is called Co-Scientist, and Co-Scientist incorporates inside a kind of generator verifier pipeline. And I've worked with that model extensively. So I guess one thing to say is that we should be careful about talking about like what is your one-shot experience playing casually with the models versus taking the best frontier models today, chaining them together with this architecture, and maybe also giving them a kind of infinite token budget, which you're never going to get if you're just using, if say you have a $20 subscription with one of these providers, they're never going to give you that infinite token budget. But like Co-Scientist has effectively like an infinite token budget. So I just think that there's a hidden level of performance that maybe most casual observers have not seen from these models.
So this generator verifier method is you have one AI generating an idea and another verifying it. Is that how it works?
Yeah, in the basic sense, it's very trivial. So it's like, okay, so for the IMO, the paper written by the UCLA team, they have about 3-page long prompts, and you can go look at them. The ones I used were much shorter, and they were basically like, okay, whatever the initial thing I'm asking, like, oh, some question about nonlinear quantum mechanics or something, right, or ADS CFT or something.
Right.
But then I feed it through subsequent steps in which I'm asking the next model to critique step by step both the mathematics, calculations, and also the logic of what was output by the previous step, and then to write either clarifying questions or corrections to what was said, and it sort of chain together things like that. And then if you close your eyes and don't look at what's happening in the middle and you just look at the output, I claim on average the final output could be substantially better than just the one-shot result.
How good do you find it is at spotting errors or things like that? Because I find if I give it something that I know has a mistake in it, it is not very good at detecting
Yeah,
error. So
yeah.
what kind of tricks do you use to get it to help verify? So I've even found that it will not even do it'll like even units. If you ask it to check the units, it will double down on something
Yeah.
rather than admit that the units are wrong. So I'm interested in how you get it to verify.
Yeah. So
Um,
one important way to inject uncorrelated variance into this process is to use different models, because the way each particular lab, whether it's OpenAI versus DeepMind versus DeepSeek or Qwen, they're training their models in different ways, and they even have slightly different training corpora, because like the Chinese labs, they have huge resources of like solved graduate school problems that are in Chinese that are used at Chinese universities. So they have kind of like somewhat orthogonal methods and also training data sets. So the way the models react to things, like one model might be very bad at order of magnitude estimates or units, and another model might be somewhat better. So I do find like a big part of the improvement is passing between different models.
I guess it feels like it's better at generating something which looks plausible than it is at detecting whether something is correct or not. I think that's my experience at least. Which
I yeah, I,
like for me, it would be useful if it was reliable, but because it's so unreliable, I find that the reason I don't use it is that I spend more time chasing something which sounds plausibly correct, and then you realize it's nonsense halfway through, and you've wasted an hour looking through it. And so I do find that in general, I'm not at the break even point because I just would spend too much time trying to verify it, and
yeah.
it's wrong so often that it's not really worth my time. But if there was a way to, computationally at least up the percentage that it's correct, that would make it more useful.
Yeah, I agree with that as well. So the worst kind of mistake that the model produces, I sort of say this in the companion paper that I wrote, is when it shows you something that's tantalizingly like plausible. You're like, oh,
Yeah.
really? Oh, Oppenheim showed this, blah, and I can use that to further reduce these equations. And then I spend a bunch of time, and then later realize I spend hours, and then I later realize no, it actually misunderstood what Oppenheim did, and just wasted a bunch of my time. So those are the most costly errors, and I do find that having another model look at it can often correct those errors, and not correct them like it does it. It just swaps in a completely correct thing for what was incorrect, but it casts doubt on the assertion that was made by the first model. So I find that is chaining together different models is quite good at that. And sometimes like I don't even read carefully the output. I just look to see whether the models are disagreeing a lot and never converge. And if they disagree a lot and never converge, I find that a moderately good signal that something like this nightmare scenario is going on. Whereas it doesn't mean nothing is like completely deterministic here. So you can't conclude anything with certainty with these models. But on the other hand, if they all converge and they're not able to find problems with the argument previously given by the other model, again, it doesn't mean that it's 100% correct, but it means that maybe it's better for me, it's worthwhile for me to invest the time to actually engage like with real thinking cycles with what the thing is saying now.
Mhm.
So I'm using everything kind of probabilistically like that.
I mean, I find that sometimes I'll do something like I'll say, "Can you give me some Mathematica to check the answer?" And it will give me something, and then I'll realize that it gave me fake Mathematica
Yeah,
that will confirm its thing. So, I find it very tricky to check. And I mean, I expect that at some point we'll break, or at least for the stuff that I do, we'll break even, and it will even become worth my while to kind of, but
yeah.
check up on it. But at the moment, it feels the verification is just really difficult.
I think thinking about it in terms of the cost benefit analysis and break even is probably the right thing for other researchers, for all of us researchers to do. And so, yeah, you should be on the lookout for, is this wasting more of my time than it's actually helping? And I guess I find with this kind of generate verify thing and some experience doing this, it's positive for me, I would say. It was negative at first. It was actually strongly negative at first. I actually got a little irritated. I shouldn't say this out loud, but the people on the scientist team at DeepMind are such wonderful people. But the way the initial stuff their model was giving me wasted so much of my time. And there was even like, just to get into some like color, it actually generate like you guys know the Strominger BMS stuff, the soft air. So it generated some suggestions that the question I was asking it about, the answer could be obtained by using this Strominger formalism and BMS stuff. And I wasted a tremendous amount of time until I realized like this is just wrong. This is just like completely misleading. And but then like my later interactions with the model, I would always subject things to quite a lot of this generate verify stuff before I myself invested a significant amount of time in pursuing any kind of deeper suggestion from the model.
So let me ask my next question based on that. What do you think changes in the next 2 to 3 years about how physicists work because of AI?
My prediction, I guess I'm optimistic. So I think that I think it's also already the case that, so you could say like, okay, I just happen to be the guy who published a paper in which a lot of the stuff in the paper came from an AI. But I do know lots of mostly skewed younger, like you, Nirmalia, younger physicists who are using the models they feel productively on a daily basis in their research. And it could be lighter weight things like Jonathan mentioned, like a literature review, or trying to get it to just explain, hey, what's new in this paper that was on the archive? It's 50 pages. And I just want to make sure, I just want to see if they actually did something that I think they might have done. And you just quickly ask the model to do. So I think there's quite a lot of engagement already, but I think the quality level will improve. I think either the labs or some third-party pro bono group of physicists will build like a better generator verifier kind of tooling, and so that the cost benefit analysis will move into the positive area for large numbers of physicists, even if they don't want to do any work to like build that tooling. I think it'll just happen, and the models fundamentally are going to get better because all the labs are trying to suck in physicists who are at the frontier and kind of can tell the difference, like at a glance, can tell the difference between model slop and wait, this is kind of interesting, or this actually could be correct. So they're trying to incorporate that into their training data sets. And so I think there's going to be continued improvement.
What about in the longer term, like 10 to 15 years? Do you think, Steve, that it can replace physicists?
That's above my pay grade.
That's
I guess I think, well, okay, I think in 10 or 15 years, physicists will be interacting very heavily with models in their work. And I also think there could come a time where, journal refereeing could be largely left to models, I think. I mean, they could become a very big part of that process. And I also think, like today, like we have an oracle named, Ed Witten or something, and people just, what Ed says, people suddenly think, even if you don't quite understand what he said, you're like, wait, if Ed said that, I'm going to go look at that because it might be interesting. I actually think, again, people may think I'm crazy, but I think in 10 or 15 years, we could end up in that state with models where AIs are just kind of saying something to the community, like the community is actually paying attention to what like the current best AI for physics model is saying about something. and people go off and they don't fully understand what the model is saying, but its signaling value is so high that it causes like trends or fashions the way that someone like Ed Witten can. That's a kind of very hypothetical prediction, but I think that could happen.
Jonathan, do you agree with that optimism?
I mean, I'm both optimistic and pessimistic at the same time. So, like take the example of refereeing, which Steve mentioned. I would worry about a world in which I think a world in which we do an initial round of refereeing. I would encourage people to do an internal round of refereeing using an LLM. You can see what rings true for you, because usually when you get a good referee report, it rings true or it doesn't. Um, and you see if you get defensive or not, or you know what I mean? So I think that's a useful thing. And I can imagine that there will be journals who will, require people to do an initial internal round of LLM refereeing. But I would be very nervous about offloading the refereeing to LLMs. And I mean, for the simple reason that I've got a slew of, incorrect papers that I give to LLMs to see what they say, and invariably they are very bad at judging it. So I think they can judge some things, but again, they're like wrong more often than they're not, and so you have to check them thoroughly and not rely on them. And I guess I also worry about the other longer term thing of, will we believe these? I feel like that we have a natural tendency. People seem to have a tendency to believe these models, even when it's very unclear why we should. And um, I I would be inclined to believe Ed Witten over an LLM. And I guess that's why I think that's why it's important to understand them now, because I think we're at this sweet spot in the history of AI and these LLMs, in that they are clearly doing stuff which is not in their training data. I think that's undeniable. And yet we can understand them, and there'll be a point, I presume, when maybe we won't understand them very easily, or less and less of us will be able to understand them. And so we're in a sweet spot in history, I think, where we can, hopefully get a better understanding of them and their fallibility and their, abilities. But I would be very reluctant to. I'm nervous about the moment when we have an LLM tell us that, some theory is the correct direction forward, and people believe that. I think that is going to be a dangerous time.
I don't think we should turn the reins over to them anytime soon. Like, definitely not anytime soon. But you were asking for a 10, 15-year
Yeah, I
prediction,
mean,
which,
that's a very long time frame, isn't it? Who knows?
yeah.
Yeah.
But
But I think people will believe it well before that 10 or 15. I mean, I think there are people right now, and I worry about this with students, especially, it seems people can rely on them quite a lot without really, even in domains when there's no reason why we should trust them. And I mean, that's true of physics, but there's going to be a lot of companies that are going to offload decisions to LLMs that are going to be regretting it. So I think that's true in many areas of our endeavors.
I want to articulate the negative AI slop nightmare scenario, because I think like this is something, maybe Jonathan is a little more focused on this than I am, but I don't want to give the impression that I discount that problem. I think it's a real problem. So you could end up in a situation where the journals get clogged with things that are subtly wrong, because the AIs can produce just such a big volume of stuff that looks pretty good, and it could get published. And maybe some people say that about my paper, but the AIs are fully capable of producing large volumes of stuff that could be subtly wrong and could clog up the journals and just totally change our sort of confidence level in what's published in journals. Another part of the nightmare scenario is our students stop having the critical ability or the calculational ability to do things on their own. Because, for example, I don't know how you guys are running your classes now, but in the old days when you would assign like a bunch of Jackson problems and the kid would hand write like, 50, we all did this, like 50 pages of solutions that we had to work through ourselves. Now I can't do that because a kid can just get the model to do it. So I don't know what that does to the training of the next generation of physicists. So I'm actually very worried about that. I mean, I think that's a huge pitfall that we have to figure out how to deal with. So I think there is a near-term world where things actively get made worse by the presence of AI. It could happen this way, that AIs and physics are not dealt with in the proper way, and the world kind of gets a little bit worse for physics rather than better. I think that's possible.
Yeah, I mean, I was discussing this with a colleague of mine. The first time you encounter a problem and you start thinking about it, that is the most precious time, because that's when you're thinking most creatively. That's when you are so confused, and that's a wonderful moment. And if people's initial first reaction is ask the LLM first, then we're losing that moment. And of course, I guess there's a way of making sure you don't do that, but also using them positively to learn things. And I guess students have that benefit that they can ask all their dumb questions to the LLM, which was something that we as students couldn't do. So there's also a huge advantage in terms of learning physics that students have. And I guess you need a bit of discipline to restrict to use it as a learning tool rather than as a cheating tool, I suppose.
I think you definitely need, I'm talking about researchers now, not students so much. Students need the discipline to like force their brain to develop its own facility with doing these things and not relying too much on the models. Of course, I sound like, maybe Greeks complaining about writing or people complaining about Mathematica 30 years ago or something, but every generation has this. But what I meant for researchers is just having epistemic discipline to like know in your mind, like, yeah, the models can get things badly wrong. I need to think it through myself. I can use the model in a certain way, but I need to have a very disciplined kind of way of thinking about how I can use the models and not let them dominate. For example, Jonathan was saying the first ideation stage, like don't let them dominate that, right? So I think there has to be some self-discipline and development of strategies for how our wetware brains deal with these things.
Do you see AI, affecting the physics job market, whether for PhD students, postdocs, or faculty?
Well, I'm a former university administrator, so I do have some thoughts on this. The really fundamental question, which I think even most faculty members haven't thought that much about, is like, what dictates fundamentally, what's the size of a physics department at a university? And so, you can have like our school has 50,000 students, and our physics department, because we have this big nuclear accelerator lab, there's just kind of like, we have kind of effectively a big department. It's like 100 faculty if you count the people that are appointed at the lab. But the core physics department maybe is 50 faculty or something, right? But that ratio of faculty to students is way lower than, say, at Caltech or Harvard or many other schools, right? So there's the question is like, what is the relationship between like how many physicists are employed versus like how many college students there are? It's not a very fundamental relationship. It has a lot to do with just path dependence at the school and how a particular dean or president views the prestige level of physics versus other fields. So there's a lot of very complicated stuff. I think if administrators figured out that undergrads are not, even if you just survey them, because I survey my students about this stuff all the time. And if they're starting to say things like, I learned better from the model than from your lecture, Steve. And if that gets to the higher administrators and they believe the students are not in error about that self-reporting, that could totally change their view. They could say, like, we don't need so many physicists teaching these kids. We can just record Jonathan's wonderful lecture, let the students listen to that, and then they can interrogate the models about what Jonathan said. And we don't need Steve at the blackboard giving effectively the same lecture here in Michigan, right? So it could evolve in a very drastic way. I don't know. But on the other hand, I don't know, maybe the physicists, if the models are really good, this is the Sam Altman view, is that eventually like the processes running at the data centers are almost as effective as human workers. So still the rate of research progress in this optimistic view could still go up, even if you are employing fewer human physicists. So I think we're in for very interesting times.
I do agree with Steve that most of our salaries are because of our teaching. So in terms of how many, so if you think of teaching, you can imagine that changing. I mean, you could imagine less universities needed. But I mean, that's not why, people don't go to universities to sit in front of a laptop and listen to a lecture and then be interrogated by an LLM. So I think, there are all kinds of other aspects to teaching in the university which require people to, show up in person. I don't see research change, it's the use of LLMs and machine learners and stuff. I feel like that's a big multiplier, and I don't see that as necessarily shrinking the number of physicists, at least in the short term, say next 5 years. But I do think it's worthwhile to like think about um, what areas of physics are going to be more fruitful because they have these tools available, or you know, um, uh, yeah. I mean, it's very interesting times, and it's hard. I think no one can really predict what's happening, but my guess is for research, it's a multiplier, whereas for teaching, you could imagine something different happening.
One of the biggest questions I have, it's a huge blind spot of mine that I've been meaning to drill down on is, we're three theorists talking, right? So the way we would use the models is, right, there's a certain way we would use the models.
Right.
I don't know how my experimental colleagues think of it in
Mhm.
terms of for their core work,
Mhm.
right? So if they're doing data analysis and they have to write some code in Python or something, like, okay, the models maybe help them write that code, but they're not going to let the LLM quote analyze their data, at least not anytime soon. Um, are they using the models to read, like, hey, what did this crazy theorist say? And is there any way I can test this in my lab? Like, does that help them interpolate between theoretical stuff that we write and things they can do in the lab? I just don't know. Like, there could be a big qualitative difference between how, and they're most of the physics community, actually.
Right.
So I don't really understand how the models is affecting their day-to-day lives.
I mean, I expect that I do think that it's able to translate theory into experiment. That is a use of it. Explain. Um,
Yeah.
and obviously, robotics is well lagging in terms of its ability. So I think you're pretty safe if you're an experimentalist. But I can imagine experiments change. There are some experiments at some point will be automated, and you could imagine material science just booming in a way that other experiments can't be. And so I could imagine certain kinds of experimental, I could imagine I could imagine us needing a lot more experimentalists in certain areas. And so the impact in some areas I can imagine being hugely positive.
Yeah. On
Also,
that
I think,
note, oh, sorry, if I could
yeah,
add
go on,
one more.
no, please,
Yeah,
please.
so one of the reasons I had a bad experience with co-scientists because the first people they had brought in to use it were mainly like in fields like biology or material science or chemistry, where there was a little bit more of a combinatorial nature
Mm.
to ideation. So, like if you're looking for a promising molecule and some drug target, but there's a huge, vast literature, and the model just reads all that literature and suggests to you, hey, based on this study, there's some chance this molecule is going to do that to this target, and maybe you should run this set of experiments, assign some grad student and some mice, to do this experiment or so. So that's what they had tuned it for, and yeah, that could have a huge impact in those areas. It was not that well tuned for like our kind of theory type stuff. But yeah, it could have an impact in other areas of science, which is just sort of qualitatively different than what we experience.
Yeah, I mean, I think our area of physics is probably the worst. It's probably the lowest impact. I mean, I
Yeah.
think for an LLM to get some, you know, shift in fundamental physics, I think that will take a lot.
Yeah.
That's many years away. So I think we're the lowest impact, but still a multiplier. So
I do think that because it's a multiplier, a lot of the easy problems, the low-hanging fruits will be taken by AI, and maybe, maybe the level of
The-
problems people working on will go up. What do you think?
I think that's true. I mean, I struggle with this with like, so I have to set the problem sets for next term for my class. And I know that they're going to use AI, some of them, unfortunately, and I try and, plead with them that they won't learn if they use AI for some of these questions. But I also want to give them questions that I will encourage them to use an AI for, because you can presumably, give them much harder questions and more open-ended questions. And it's the same with the master's thesis, what becomes possible for a master's thesis with use of an LLM. Because I do think that in terms of, say, a master's thesis, an LLM is around at that level. I think it's a huge, you expect a lot more now of students, I think, if they're going to use a tool like this. So yes, it'll get some low-hanging fruit, but that hopefully means people can aim higher. And I guess the issue of slop is that people won't, and we'll just get a lot of, you know, proof of minor Erdos theorems and things like this. I mean,
well, I have to comment on the Erdos thing because I've never, like, my taste is such that I've never been that interested in Erdos type problems.
Mhm.
But if you read like Terry Tao's blog about how excited he is that he and a collaboration of 5 other math guys using Lean and the models were finally able to crack this Erdos problem, like they seem to think it's a big deal. So
Yeah, no, indeed, indeed.
yeah.
But I mean, it's interesting that it's mathematicians who have been most excited about the use of these models, and I think that is because they can verify it with Lean.
Yeah.
So I guess the question is, as physicists, can we come up with something that, okay, it can't be something like Lean and verify it in as formal a way, but maybe there are tools that can be used to at least have a bit more confidence in results, which I think is the issue. I think they don't have that problem. They can, once, if they can formally verify it something, they're
Yeah.
laughing.
Well,
So,
they
I think
often
that's
don't.
why they're so excited. I think that's why the mathematicians have all been so incredibly excited, much more ahead of the game, I think, than physicists.
Yeah, I think they don't even need Lean because, like, a good human mathematician can still go through the proof and
Right.
see if it makes sense. And in the case with the IMO problems, like, a human could grade the problems and
Right.
see that, yeah, wow, this model is actually able to solve almost all the IMO problems. So
Right. But I think physics is just a very different beast to mathematics. It's not like there's these well-defined questions necessarily, or that there is you know, figuring out what an interesting answer is. And I mean, that's true in mathematics as well. But I think physics is just a bit fuzzier, which makes it harder for it to be automated in the same way.
yeah, I agree with you.
Let's now talk about the paper. Let's get into that. So this is about nonlinear quantum mechanics, which, to my knowledge, was first introduced by Steven Weinberg in the 80s. So I'm going to come to you, Jonathan. And what is nonlinear quantum mechanics, and why was it like not a viable idea?
Well, I mean, it's interesting. So I think Weinberg was interested in modifying the dynamics of quantum mechanics. So, you have the Schrödinger equation, where the evolution is linear in the quantum state, or if you think about it in terms of a density matrix, the evolution is linear in the density matrix. And he was interested in this question of whether you could modify the Schrödinger equation in order to make it nonlinear. And what Jizen and Polchinski essentially showed is that if you modify the dynamics of quantum mechanics, you're also just modifying everything. You're modifying the rules, how you compute probabilities, what the density matrix of quantum mechanics means. So the whole formalism just kind of falls apart. And I think that was the surprise, and maybe the surprise. And with it, there's still, I think, within the high energy physics community, there's still every now and then there's still these attempts to examine nonlinear mechanics. But I think from the quantum information community in particular, for example, I think it was just viewed as breaking all of quantum mechanics so badly that there's no way you can ever fix it.
I might be the oldest guy on this call, so I could give you maybe a little bit more color on the history of this. So I was already I think I was I had a PhD, or I was around that time when Weinberg wrote his paper on this, which is called Testing Quantum Mechanics. But there's a prehistory to this, which is that, for example, for a long time, people in quantum foundations were interested in, like, is there such a thing as dynamical collapse of the wave function?
Right.
Which I think is an honest thing. Like, okay, it's very much in disfavor today, that I think a lot of moderns would just say, that's crazy, that can never be possible. But there were a lot of physicists who thought about this, and they wrote down honest models, which of course had to be nonlinear, which, in some toy few particle system, they would have dynamical collapse of the wave function. Maybe that's not correct, that it has to be nonlinear, but there were models that people proposed that were nonlinear, in which wave functions actually collapsed, right?
Well, I think those are slightly different, though, Steve, because I think those are nonlinear in it if you look at a particular trajectory, but then when you average them over all possible trajectories, they still behave linearly. I mean, you may be able to get other ones which aren't, but I think there are, I think even in the stochastic collapse community, I would say on if you average over all possible trajectories, you should still get something linear. And I think most models are
Yeah.
linear in that sense.
Well, I think that's true of stochastic collapse, but I thought there were people who actually wrote models where, if based on the actual dynamics of the wave function, it would all the probability weight would like flow into something, and it looked like actual collapse.
Okay.
But it's maybe a different vein of
Right.
research we're talking about. But anyway, I do remember the idea that quantum mechanics should be nonlinear preceding Weinberg writing his paper.
Yeah, I think that's true.
Weinberg came up with a very nice example, which I think Jonathan, in his critique of my paper, has rightly pointed out. Like, this is maybe the one that gets to the core of it, where it's nonlinear, but it's sort of hyper local. So like the way the evolution of the state is modified only depends on the expectation value and action of an operator at that point in space-time. And so Weinberg was the one who like proposed that form, and that form has a lot of really good, pleasing properties. But I think you could even find, like, relatively recent, like in the last 5 years, people either from high energy or from Quantum Foundation still writing papers on, not that many, but papers on nonlinear modifications of quantum mechanics, which are not necessarily of that precise Weinberg form. So,
I mean, I mean, in the literature of, like, for example, people that consider, so I'm interested in studying theories in which space-time is treated classically. And within that community, there are people that look at nonlinear versions of that, something called the semi-classical Einstein's equation. And so that's a nonlinear set of equations. It's pathological in my view, and we should, move as far away from it as possible. But so there are indeed lots of people that study it. And I guess that is I mean, maybe that was partly behind my reaction, which is just that, there are these people that study them, but we should. I think there is some interest in them. There's clearly an interest in them, but there is, I think, not a recognition of how much they modify quantum mechanics, how much trouble they get you in, and how in some sense how everything just falls apart as soon as you do them. And so I think that was maybe partly behind my reaction to, like, no, let's not study nonlinear quantum mechanics. At the same time, what was I found interesting when because I when you came up with this paper, and when I was thinking about it, I reread Gizen and Polchinski, who critiqued Weinberg's nonlinear model, and was just reminded of what a beautiful and, in some sense, mysterious set of papers that they are, because I think it is quite remarkable that something that is local theory, local Hamiltonian, even though dynamically it's local, it produces something which just violates locality in such a bad way, and so it really shows you how tightly quantum mechanics holds together and how difficult it is to modify. And the proof that it fails is so beautiful. So I mean, I was grateful that I was reminded of this.
Yeah, I want to say I agree with you, Jonathan. I think the lesson is that there's probably not any small modification. Well, Weinberg has sort of said this in so many words over the years. Like, there's no small modification of quantum mechanics that he knows of that isn't going to break it completely.
Right.
And I remember when Joe's paper came out, I think it was in Physical Review Letters. It's very short, and I think it has the word Everett phone
Yes.
in the paper, which was very mysterious to me at the time. And actually, one of the benefits of the models is I can get a model. Like at the time, I did not understand that paper when I was a student. I think I was a student or just finished my PhD when that paper came out, and I did not understand what he was saying because I didn't really know what Everett was, and so anyway, so now I can get a model to like very, very cleanly explain to me what is in those papers, right? Which I think is for students super beneficial. Yeah, so I kind of agree with you, Jonathan, that like there isn't like one probably shouldn't be thinking that much about nonlinear quantum mechanics as it's there's no like reasonable model that you can write down. I think there's no reasonable model that you can write down that
Right.
implements it. On the other hand, I feel like if you really believe that, if that's your posterior after all this study, then it is very remarkable, right? Because that is, I think this is the one thing in nature that at least you're sure of is absolutely linear, right? Like, do we know any other examples of things in the laws of physics that are absolutely linear? Like, it's kind of an amazing result. And just quick, add one more thing before you react. Like, I've always wondered, since we don't really know how quantum gravity is going to turn out, is there some loophole that can come from quantum gravity, which maybe the low energy effective field theory still has to be linear quantum mechanics, but maybe there's something going on in the quantum dynamics. And back in the early days of string theory, there was this big question of like, well, you guys are solving quantum gravity. Is it still plain old linear quantum mechanics of strings, or is it something else? And that was, I remember in the early days of string theory, that was still a thing people actually talked about, whether string theory was going to introduce something really radically different to the way quantum mechanics actually works, or if it's just going to be, no, quantum mechanics is completely unaltered by string theory, and it's still just linear quantum mechanics. So anyway, I'll let you react to what I said.
Yeah, I mean, I think it's interesting to consider modifications to quantum mechanics. I think there's a reason that it has to be linear, and it's also true in classical mechanics that it has to be like things have to be linear in probabilities, and this is also true in classical mechanics. If I flip a coin and if it's heads, I put a planet on the right, and if it's tails, I put it on the left, then the evolution of that probability distribution of planets has to be the same whether I know what the value of the coin toss was or if I don't know what the value of the coin toss was. And so linearity just reflects the fact that the dynamics of these two planets, of the one planet, whether it's on the left or the right, should somehow not depend on whether I know the value of the coin toss and where I put the planet. And that's just because if physics does not obey that law, then what that means is that the evolution is different based on a counterfactual. The evolution when the planet is on the left somehow depends on where I would have put the planet had the coin come out with a different result. And we know that physics cannot depend on what I would have done had the coin been a different value,
Yes.
because I didn't, because it was heads, and it doesn't matter what I would have done had the coin come out tails. So that linearity in quantum mechanics and for classical mechanics, if I have probability distributions, reflects that fact. And I think that feels like a fact about probabilities that we just don't want to mess with, because you're really messing with some deep stuff, I think, that goes well beyond a kind of is embedded very deep in just what it means to consider probability distributions rather than anything to do with quantum mechanics or anything else. So even if I were to come up with some, theory that is more fundamental than quantum mechanics, it should still obey this kind of a linearity, that on probability distributions, it should not depend on whether I know the value of the coin toss. Sorry, that was a bit of a TED talk, I think.
Yeah, no, I would like to follow up with you about that maybe somewhere else, because I think we might lose all of our one listener, if I go further into what you just said.
It's okay, it's Normalia's listener, so
But yeah, maybe we should let Nirmalya drive.
I wanted to ask, like, you had also worked on nonlinear quantum mechanics before. So what made you like revisit the problem with AI?
Yeah, so thanks for asking that, and maybe this is good for something Jonathan might be interested in. So when I worked on it 10 years ago, that paper is from 2014. I was interested in the question of whether if you try to do full blown quantum field theory with nonlinear modifications, is there anything beyond what Giesen and Polchinski had already said? Like, is there anything special to the fact that it's now a field that the state vector is describing is an amplitude for the state of an entire quantum field, which is valued everywhere in space-time? Is there anything special that results? And so we were trying to think that through. We were looking at a much more general class of nonlinear modifications than just that Weinberg term, because there were things in the literature. The first thing we did, obviously, even back then, was we just went and looked and saw like what are the class of models people are thinking about in terms of nonlinear modifications of quantum mechanics, and then like what are the field theoretic analogs of those models and how do they behave? And we came upon this weird behavior that if you just take a coherent state wave packet at A and another one at B, and they were in a product state, but then you let the thing evolve forward a little bit, they would get entangled instantaneously with each other. Now, I think, Jonathan, I still have to answer the email you sent me about this. I think for the Weinberg term, that doesn't happen. But for the other models that we consider, the general class of models that we were looking at, that did happen. So anyway, we got interested in this, I don't know, maybe a very esoteric question. And then the only reason I was asking GPT-5 about this was just because I have this general algorithm for understanding how good the models are, which is very similar to what Jonathan said earlier, which is like I have some problems which have been solved but not published, and I can test the models on that because they're probably not looking up the answer, right? It's the same reason why for the IMO problems they have to wait until like each year they have the IMO competition and the problem committee generates like 6 novel, quote, at least somewhat novel problems, and they can test the models on those. So in my case, having written a lot of papers, for every paper, there's always some stuff that you didn't follow up on. Like you did what you could do, and then you decided, okay, at this point it's a paper, and I publish it. But there's some other stuff that you were looking at. So there's some stuff that wasn't in the actual published paper. There's some stuff that you wonder about because you didn't nail it down, or maybe if you had a new student come in, you would say, hey, can you go back and look at this? So that was a way that I was just testing the models, because I would test to see whether the model understood what we had done in the paper, but then I would start asking questions about things that I had thought about that weren't published. And it's just a way of testing the models. And I was just very flabbergasted when it just spat out this thing like, oh, by the way, I can do this. Do you want me to do it? And I'm like, yeah, sure, do it. So that's how this whole thing started.
So can you briefly explain what that was and what was the result of your paper? Like if you could summarize your paper.
So I was asking it about like, is there anything special about trying to do quantum mechanics of fields and having relativistic covariance that's different from just looking at quantum mechanics of a few degrees of freedom, and maybe you're not explicitly imposing relativistic invariance on the Hamiltonian or the system. And so that was where I was starting to question it. And it suggested that this Tominaga-Schwinger formalism, which was invented by Tominaga-Schwinger back in the day, like this is in a sense like the invention of field theory, this idea that if you want the thing to be relativistically covariant, it has to be invariant under different possible time slicing. So like if I choose some particular time slicing, there's some coordinate transformation I can make where the time is just, the time coordinate is a little bit different, and there still should be some relativistic covariance properties of the resulting theory. And that's, so Tominaga and Schwinger had written down a certain commutation relation that had to do with like sort of deforming time a little bit, the flow of time a little bit in, say, two space-like separated regions. And that shouldn't affect the physical results of the theory. And the model just said, well, I should just take the Tominaga-Schwinger evolution equation, add the nonlinear term, and then test it against these integrability or foliation invariance conditions. And then it actually just like cranked out the equations, which I think turned out to be correct. And so I just thought, well, that's interesting. Where does this all go? And that's how it all started. And I could analogize this, by the way, to like, I mean, I could have a colleague or a student, like if I were just explaining like, oh, we did this in this old paper and kind of we were trying to get at this question. And then the colleague just says to me, oh, well, have you looked at what the nonlinear term does to the Tomonaga-Schwinger equations? And like, if he could write it like lightning speed on my whiteboard, he might have just like done that. And so that could have happened with a human actually. But I was quite fascinated that it happened with a model. So.
And here you use the generator-verifier method. In fact, you have written a companion paper where you describe the process. And so you use the generator-verifier method, and it came out with the result.
Yeah, so the research process involved, I used 3 models heavily, and then there were a couple other ones that I would occasionally use. And I even at the end ran the whole thing through co-scientist. And there were, I mean, if you want the whole narrative, there was a place where the models really made a very deep conceptual mistake where it claimed it could prove something using axiomatic field theory. And I was very intrigued by that. I'm not an expert in axiomatic field theory. And I had to like learn a bunch of stuff about the Riesch-Schleider theorem and stuff like this to understand what the model was claiming. And after a while, I figured out the model was probably wrong about this. And interestingly, when I ran that line of attack through the generator verifier model, the models never converge. Like one model would say, the model 1 is totally wrong because of this, and so like that was an interesting signal that like it wasn't really, it was sort of just hallucinating or confabulating. It had sucked me in because of my lack of expertise on the new technology it was trying to bring into the attack. So yeah, but for lots of other things, the model was extremely useful in just pushing through the paper and working through examples and stuff like that. And also ultimately, the referee wanted me to look at the KR model, David E. Kaplan and his collaborators, I think Rajendran is his name. So the referee wanted me to look at the KR model, and the models were able to actually process the KR model through the TS, the Tomonaga-Schwinger conditions very quickly, and actually figured out something kind of geometrical, which I thought was interesting. And only one of the models was capable of that. The other models got the wrong answer. But then when I ran it through the generator verifier loop, they all converged. So, but I don't know, it was a pretty interesting experiment for me in terms of use of models. So,
but that part was all model, that calculation of KR model, that was done by model.
It was because I was like, how you are. Well, I am when I get the referee report. I'm like, referee, it's referees like trying to force you to do all this work, like, or like trying to like, hey, you and him fight, like you and KR start fighting because I want you to like battle with K. I don't think it was K and R that refereed my paper, but like you and KR, now you guys fight, right? And I was like, oh shit, okay. And I was kind of lazy. I was in a low energy moment when I got the referee report, so I just like asked the model about it. I was like, hey, can you check whether KR model satisfies? And and it did it perfect. GPT-5 did it perfectly. The other models screwed it up, but I was able to get the answer, I think, correct answer pretty quickly this way.
That was pretty impressive, I would say, for a model.
Yeah, and even this notation of the the set, which is defined by the past light cone of this point, like that notation is better than the notation I probably would have invented if I had to write the whole thing up myself. So, yeah.
Jonathan, you have criticized this paper. You have said that the criteria that AI has discovered actually does not test for nonlinearity so much as non-locality. So if you want to expand on that.
Yeah, sure. I'd be interested if Steve agrees or not. But I mean, there are 2 reasons why a theory can turn out to violate Lorentz invariance or relativity. One is because if it's like Weinberg's model, it's nonlinear and local, and the other one is that the Hamiltonian is not local. And the paper was about nonlinearity violating a criteria for when a nonlinear modification violates relativity, and yet the condition was actually testing something else, whether a non-local Hamiltonian ends up violating relativity. So it seems to me that the criteria, the model claimed to come up with a criteria for whether nonlinear quantum mechanics violates relativity, but instead came up with a criteria for something completely different. And so um, I suppose that's my critique, is just that it's a category error for what the criteria was. And I guess I thought it was interesting that we, to some extent, had this, we have this criteria for whether nonlinear quantum mechanics violates relativity, which is this proof due to Jazin and Polchinski. And that ought to be in the training data. That's, a paper from a 35-year-old paper and highly cited. And it somehow didn't seem, at least, to pick up on that. And maybe, I tell I think there are blind spots in these models. I mean, in some sense, it's remarkable we're having this discussion, right? Like I feel like I have these two parallel thoughts always going on, which is I can't believe the model was so stupid. And at the same time, it's like, wow, I can't believe I'm having this discussion about the model missing something, because it's just amazing that it can do anything. Um, but yeah, I do think that it's interesting that even though the correct solution is in its training data, clearly it somehow misses this. And I guess that is, that is my critique. And yeah, I would be interested in if Steve agrees or not. But
So I think the distinction that Jonathan makes is very subtle, but it's correct. I mean, it's correct that even this sort of super local Weinberg version of modification will fail I sorry if I'm pronouncing the guy's name wrong, Jason Polchinski GP. It'll fail the GP. It'll have these bad properties that GP identified, and all the models that I look at in the paper will have this bad property. I think that AIs understood this, but I think they were pushing a certain direction, because I was like, well, I was specifically asking for like, analyze these models in a quantum field theory context. And so that's probably why it went over to get the Tomonaga-Schwinger stuff and bring it back. But I agree with your point that when it fails these conditions, it's failing it because the actual form of the quote term that's added to the quantum evolution is both nonlinear and non-local, and the way it fails the TS equations is because of the non-locality. I think that's your point, right? And so I think that's fair. But I think the model did analyze models of nonlinear quantum mechanics, which are in the literature, applied to field theory and using some criterion for relativistic covariance. So it did do that, and I think it was not unaware that of GP. But it didn't say like, hey, by the way, Steve, all these models fail GP. Why are you even interested in this other thing? Like, it never said that to me. But maybe that's my failing. Like, I think Jonathan would say, like, Steve, if I had probably gone down the hall and talked to Jonathan while I was working, he would have been like, why are you even interested in this other thing? Because they all fail GP, which I don't disagree with that, actually. I mean, but I think that's a little bit a question of taste. Like whether there's still something interesting that's happening here or not.
Well,
For example, the
there's
KR.
something interesting. So I think it's interesting, for example, that the model you looked at is a DK model, or KR model. It fails both. It violates relativity because it's nonlinear, and it also violates it because it's a non-local Hamiltonian. So that is probably, this model is in the literature. It's reasonably well cited, and so it's probably good to catch that. I guess what is interesting, so because I'm interested in verification, it's kind of interesting, like, what is it that made the model unable to recognize that that there's an error in some sense, or that it's applying the wrong criteria. And as a human, you look at this and you say, oh, well, entanglement is not mentioned in this as a criteria, and entanglement is definitely what is required. And so why didn't the model, because it's just pattern matching, why doesn't it know about entanglement? Why doesn't a verifier ping that entanglement is not being is not a requirement here? So I think it's kind of, interesting. And indeed, when I gave the paper to LLMs, they don't catch these sorts of things. So for me, this is the kind of difficulty in that um, it's so hard to verify them because the models are putting out all, it's quite, I didn't either. You look at this thing and it's very complicated initially when you first look at it. It's slightly intimidating and you kind of don't kind of examine it in the same critical way you might, normally. And so for me, that was the interesting aspect of it, I suppose.
I don't think on any of these points, Jonathan and I disagree.
Yeah.
I think we might disagree as a matter of taste of just like whether the stuff in the paper is interesting or not. I still find it interesting. So,
I mean,
um,
that is the most important criteria for
yeah,
whether. I mean, I think
yeah,
it's very dangerous to tell somebody what is in, and I do regret some of the things I have said. In that, I think it's I don't think one should, people should. What is interesting is very much a matter of taste, and there's definitely aspects of this that I've since been drawn to in terms of interesting, and so I think there are interesting aspects here. And like I said, I'm very grateful for it bringing me in contact with these proofs, which are very beautiful and I think mysterious in some ways. So um,
could I just mention that I don't want to, I don't, K and R are not here to defend themselves. So, and I think we have had some email correspondence with them. So,
yeah,
I mean, they might still maintain their model is okay. I kind of feel like their model fails, as John would say, both the nonlinear quantum mechanics. Well, sorry, what's the right way to say? Fails both the GP test and the what I would call the TS test, right? Um, but they clearly didn't think so, and I think they've written like multiple papers on this, and even like using it to like solve the hierarchy problem in some more recent paper,
right.
and they actually, sorry to get in the weeds, but this is the physics discussion. So they deliberately built their nonlinear term to integrate over the past light cone of the place where it's modifying the quantum evolution. And I think they did that because they thought that got them out of the, if I read the paper right, maybe I misunderstood it, but I think they wrote it that they built the model that way to avoid the GP problem. I don't know, maybe I misunderstand their paper completely, but I'm actually very tentative about like telling anybody their stuff is completely wrong. Like the referee made me do that calculation, and I did, the model did that calculation. I reported in my paper, but I would love it if they would actually come on and say like, yes, we agree with Jonathan and Steve, or like, no, our model is actually still okay. So I don't know. I just want to be cautious about that point. But for me, like the models, the paper I wrote did identify something interesting about the KR models, which I think otherwise I never would have noticed, or I don't know, because their model looks like it could be relativistically
Right.
covariant, but upon further examination, it has some issues, I think.
I agree with that.
Criticism that I had pointed out to you, Steve, is this old paper by Torre and Varadarajan. And they basically showed that there are problems with the Monacus-Finger approach itself, which is that if you deform these time slices and if you demand like the state evolves in a single Hilbert space, then this time evolution is not unitary. So what are your current thoughts on that? And also, let me ask, like, since this was also a paper which was probably in the AI's training data, why do you think this was missed by AI?
Yeah, so the second one, let me answer that first. Like, yeah, I don't have an answer for why, because as I stated the chronology of this, the model suggested the TS formulation as a way to examine the effects of nonlinearity in quantum field theory. And if the model had sort of deeply absorbed the idea from, is it let me call them TV, the TV paper that you just mentioned, because I can't pronounce the second guy's name. Um, if the model had deeply absorbed that conclusion, just said like the TS formulation doesn't make any sense. So if it had absorbed that, it would not have reported. It would not have suggested that as an interesting avenue of investigation. So that's an unresolved question of whether that paper, which is I think fairly well cited, and it's a well known paper, like kind of more in the, I want to say, quantum gravity community, maybe
Yeah.
not so much in the field theory
Yeah.
community. It's a little bit formal. I think we can ask, like, to what extent the model, when it synthesizes its whole picture of physics, if there's some contradictory stuff, or maybe like a bunch of papers still doing X and some paper out here that said X is crazy, don't do X, how the model integrates all that into its view of physics, it's mysterious. I don't know. Clearly, in this case, the model was just not that influenced by the TV paper. I mean, just observably based on how it reacted, right? So, and it never ever mentioned to me as I was querying it, because we got into lots of stuff about axiomatic, because of this wild goose chase that it sent me on. Lots of stuff about axiomatic quantum field theory and how that interacts with nonlinearity, but it never mentioned the TV paper. So I don't know. That's just some lacuna.
I mean, I think it's dangerous to think of it. Well, actually, I have no idea. Like, I wouldn't think of it as it having a model of physics in its head where it kind of has these plausible areas and thinks these other areas are not so, are tainted. Maybe I'm not sure that they do that. But I guess what is interesting is that here, just by word association, you might have imagined that it would, you know, recognize these things. So if because this if it gives you a Twanger-Schwinger criteria, and yet it knows that this is being criticized by other authors, you might think that those words would come out of it at some point. Or if it knows that nonlinearity and entanglement are almost always mentioned side by side, you would think that that would appear at some point in the discussion. And I guess maybe a question is how we kind of trigger those sorts of associations. I mean, you mentioned, for example, the Reach-Leader theorem, and that it mentioned that, and I half wondered when I heard that whether, the Reach-Leader theorem famously shows that, every area, even the smallest region has to be maximally entangled in some sense. And so there was a part of me that wondered whether it was mentioning that because it was somehow triggered by some notion of entanglement. And so I guess maybe one question is how, given that that this is an example where there were these word associations in its training data, why didn't they appear? And is there other ways that we can trigger them to be very critical about the thing, and especially if we're interested in some verifier model where it's going to suggest an idea, get verified, suggest an idea, get verified. How do you trigger a critical view of it? And I feel like that's very hard. I usually, when I try and talk to it, it really wants to please you, and it really wants to kind of validate your ideas. And how do you, sometimes I'll pretend that I know that there's a mistake, or sometimes I'll pretend that I think something, I'll pretend I have a hold of view that I don't actually hold. But it is tricky, and I guess I'd be interested in hearing from other people as to what kind of techniques work in order to get it to have a more critical view of any idea, for example.
Well, just reacting to a couple of points that you brought up, which I thought were really good. Yes, it's wrong for me to say the thing has a model of like a worldview of physics or something. Like, it doesn't have anything like that. But it, first of all, describing it that way is a little bit aspirational, because maybe in the future, the future AIs would have that. But this one, at this level, they don't. They clearly don't. But what's interesting, I find, about whether it anchors on some particular set of results or facts in the research literature, there's sort of two different ways it can get there. One is in the reasoning steps, if it's searching. So some of the models have built in, as they're trying to answer your question, they're searching. So they're like looking on the archive, or and as you said, sometimes there will be word associations that surface some paper, which the model might actually read in real time and put into context, and then use it to answer your question. But then at a deeper level, there could be actual connections in the pre-trained neural net model, which link, the TV critique to the Tomonaga-Schwinger thing. And those would be unavoidable, even if the way the search results came back in the process of thinking didn't surface it. It's already like encoded in some deeper way, a rigid way in the model. So I think it's very tricky to understand what's actually causing them to behave the way they behave. But one thing I've found is that a big determinant of variance in the way that they respond is like actually what they find when they search. So you're asking it to do something, and it's doing some good faith searching, trying to like surface things that are useful to respond to you. And sometimes it's that search algorithm, the way that actual search result returns things, that strongly influences what the model finally brings back to you. So in this case, I don't know the answer. Coming back to Nirmalia's question about the TV result. So my understanding of the TV result is that it's a pretty formal result, and the idea that there can't be one Hilbert space that describes the quantum field state at, say, different time slices or on different Cauchy surfaces. It's a pretty formal result, which I think is only true when you take the cutoff to infinity and the number of modes to infinity. And from the modern kind of effective field theory language, now those guys might just say, hey, you guys are not rigorous. How dare you critique my rigorous result with like this fuzzy quantum effective field theory thinking. But I think most people who work in quantum field theory who are not very formal would say, well, we don't think there's actually an infinite number of degrees of freedom. There's some cutoff. We're dealing with an effective theory. I should be able to just slightly perturb my Cauchy surface and not cause havoc, not force myself into some completely different Hilbert space, right? And even if that's true formally, when I try to do quantum field theory with an infinite number of degrees of freedom and a cutoff that's taken to zero, right? So I still feel if somebody were doing like proposing a model and I just looked at whether it satisfies, say, a model for particle physics, and it didn't satisfy this foliation independence condition, I would be concerned about that model. That would make me less interested in studying that model. I would consider that a real issue that the proposers of that model would have to deal with, TV notwithstanding. So I understand they have a result. I'm not sure what that result implies for effective field theories that we are mainly interested in.
So let's kind of summarize everything now. So what do we think is the strengths and weaknesses of AI based on this this discussion of the paper? So if I try to summarize it, we see that AI is able to come up with novel ideas like the TS criterion that Steve found. But also it is kind of sometimes it doesn't know fully about the literature. It doesn't flag things that maybe it should flag, like both for the GP example and the TV example. And as both of you kind of agree, it probably doesn't have like a model of all of physics. So that's where probably things stand. Do you think this will improve in the future? Do you agree with the summary? And do you think it will improve in the future? So I'll start with Steve.
I agree with what the points you raise in the summary. I think things will improve. I don't know how fast or how far, but I guess I'm kind of optimistic about where we'll be with AI and physics 5 or 10 years from now for sure. And maybe in the next few years, there could even be some nonlinear bending in terms of improvements of the models. I want to emphasize one thing that I think we didn't say during this conversation, which is that in the AI research community, there's this question of whether LLMs can actually reason or whether they just generate text that looks like human reasoning, which there's a subtle difference between those two things. I lean more toward the second thing, that the models generate text that looks like human reasoning. They're not reasoning the way Lean reasons, okay? And they're not good at that at this stage. They might later become better, or you could attach Lean as a module to an LLM. But that limitation is a very big limitation. That's one of the reasons I'm not that optimistic about what people normally think of as AGI in the near future, because the models are really only doing what I described. But it doesn't mean they couldn't be a useful tool for us. So I still feel it's a useful tool for doing research, but it just has to be employed in a very careful way.
Jonathan?
I'm not sure that they're yet at the point of producing like novel ideas. But I mean, I guess if you produce lots of ideas, some of them, you produce lots of ideas, and some of them will be correct. But because they require so much, sorting and sifting through that, then I'm not sure that I would count that as as coming up with novel ideas. That doesn't mean that they won't, and the rate of improving is impressive. So I would hold back on that, but I guess with me at least, this is I don't work on AI in any way, and the best I can say is I'm adjacent, and I have colleagues that do, and everything. I have no reason to they are all look like they've seen God and are and I have no reason to doubt the sincerity of that. So I think there is a perception out there that this is some hype or etc. I don't hold that view at all, but I think I think there will be a kind of at the moment we're just at the beginning where there's going to be just a lot of you know, more slop than novel ideas, but one expects maybe even in a year. I mean, you almost like every time a new model comes out, it's like maybe this time, and I eagerly try them. So anything you say can be out of date in a week. So I guess that's what makes it so exciting.
So let me ask one last question to both of you, and I'll start with you, Jonathan. What would you advise a young graduate student, someone who's just starting out now, someone who's looking at AIs, and like what would your advice to them be about AI?
Become an electrician. That seems to be a safe and valuable skill. No, I mean, in terms of, I think learning the tools is just, it's a bit like if you were born at the age when the telescope had just been invented. This is an exciting new tool, and so it's important to understand it and learn it and use it. And at the same time, you need to do it in a way that doesn't destroy your critical faculties, and that's the trick. And I mean, I viewed it more as an exciting thing rather than as something which we should be, I think there obviously is a lot of anxiety about people's jobs, and that's understandable and warranted as well. But there also is the excitement, and I think it's worthwhile learning the tools and thinking about what are the areas where they can be used to make an impact. I think that's just as you would any other new invention that comes along in physics, and which physics has always been revolutionized by when new tools come into existence. So we're about to have quantum compute. We will be having quantum computers maybe even on the same time scale. So it's a very exciting time to be doing physics, in my view.
Steve?
I think I would advise students to spend time with the models to learn what their capabilities and limitations are. I think the other main advice I would give them is have the discipline to learn to do all these calculations and stuff yourself. Do not allow yourself to rely too much on these models. And there's just no substitute for having that capability in your own brain. That's the thing I worry most about. Well, I guess I worry about two things. One is that students won't develop their own capabilities because the models make them lazy. And the other one is this short-term flood of AI slop. I do think that is a real problem that could happen. And maybe I'm maybe I'm the number one guilty person. I don't know. But yes, those are the two things that I'm worried about.
Okay, so thanks, Steve and Jonathan, for joining me today. This was a great discussion. So thank you both.
Thank you.
Thank you.
Thank you very
I
much.
enjoyed it. Yeah.